Hello all and welcome to this super useful lecture on matrix determinant. In this lecture we are going to see that what is a matrix determinant, how to calculate it, what properties it has and what relation it shares with eigenvalues. So this one is going to be very important for your fundamental understanding. Hence I request you to please pay attention and let's get started. So before covering the theory part, let's go ahead and try to see that how do we calculate the determinant of any given matrix manually, and then we will jump back to the theory part so that it makes more sense for us. So we will start by understanding that how to calculate the determinant for a 2 by 2 matrix, which is the simplest by the way. So for example, I have taken this matrix A which has 4 elements, so it is a 2 by 2 matrix, and in order to calculate its determinant, what we need to do is first we need to multiply these two elements which are diagonally to each other. So I have multiplied 2 and 1, and then we minus it with the product of these two elements diagonally with each other, which is minus 3 and 5 that we have here. After doing the calculation, we can see that the value we get is 17, which is nothing but the determinant for this matrix A. Pretty much simple and straightforward. Now let's have another example of this matrix B, which is a singular matrix by the way, and if you are following along with this playlist, then I'm pretty sure that you are already aware of the concept of a singular matrix and the fact that in linear algebra we can have only 3 types of output, which is one solution, no solution, or infinite number of solution. And this matrix that we have here is the singular matrix, which is an example of a no solution kind of output, because these two vectors or columns are dependent to each other. As you can see, the second vector is the multiple of the first one, and when we try to calculate the determinant for this singular matrix, the output comes out to be 0, which essentially means that whenever we try to calculate the determinant for any singular matrix, the output will always be 0. And this holds certain properties actually that we will discuss going forward. But at least so far we are familiar that how do we calculate the determinant for a 2 by 2 matrix. It gets more and more difficult when we try to calculate the determinant for a matrix of a bigger size. So in order to have more understanding around that, we will also have an example of determinant calculation for a 3 by 3 matrix. So here we go. We have another example of matrix A, which this time is a 3 by 3 matrix. And by the way, let me tell you that the matrix has to be a square one in order to calculate its determinant, which means the number of rows and columns has to be equal. Okay, now let's go ahead and see that how do you calculate the determinant for this one. By the way, don't get overwhelmed going by the solution we have here, because let me tell you that nobody in the field of machine learning or data science will ever ask you to calculate the determinant of any matrix by yourself manually on a pen and paper. It will be mostly done by your choice of library from a programming language like Python or R. I'm showing you these calculations just for an intuitive understanding and nothing else. Okay, now in order to calculate the determinant for this one, let's go by the first element, which is 2. And when we are considering it, we will have to neglect the corresponding rows and columns. So we are going to neglect this row and this column, and we will consider only 2 which we have here, and then we will do a simple determinant calculation for this subset of the matrix, which is a 2 by 2 matrix. So that we have already understood so far. This will be the calculation for the subset of that matrix, where I am multiplying these two elements and then I am subtracting that with the product of these two elements. Secondly, we consider the next element, which is 5, and again we will exclude the top row and the corresponding column. So we will take 5 and put it here, and then we will calculate the determinant for these 4 elements, which is 3 multiplied by 2 minus 6 multiplied by 1. So here we have minus 3 multiplied by 2 and then 6 multiplied by 1. And yes, you guessed it right. Now the same thing will happen with the last element, which is 3, and we are now going to exclude the top row again and the corresponding column. So we have considered 3 here, and then we will do the determinant calculation for these 4 elements. So minus 3 multiplied by minus 4 and 2 multiplied by 1 that we have here. And also pay attention that every time we are alternating the functions here, so first we will start by a minus and then we will add, and depending upon the size of the matrix for which you are trying to calculate the determinant, this will keep going on. So if we start with a minus, by the way, you will have to start with a minus, and then next will be plus, and then again you will have a minus and then plus, and so on. And now it becomes pretty much straightforward to do the calculation for this simple equation, and we get 146 as an output. Alright, so now I believe that you are quite comfortable around understanding that how do we calculate the determinant for a 2x2 or 3x3 matrix. We are not going to have the examples of determinant calculation for matrices of higher sizes, otherwise the length of this video will exceed too much. And also that is not necessary as well, because as I have already said earlier, all these calculations will be done by a programming language all the times in your day-to-day job. And now we are good to go to move ahead to the theory part, so that we can understand that what is the significance of a matrix determinant. So matrix determinant is the idea of mapping a square matrix to a scalar value that we have already seen. If we have 3x3 or 2x2 or any size of square matrix that gets reduced to a scalar value, and determinant of a matrix X will be denoted as this determinant then X inside the parenthesis, and it actually allows us to determine whether a matrix can be inverted or not. Essentially, if the determinant of a given matrix comes out to be 0, like we have seen in the case of a singular matrix, in that case inverse of that matrix cannot be computed. And that is quite obvious as well, because you can never calculate 1 by 0. This will be undefined. Also, if you have not seen the video on inverse matrix, then I suggest that you check it out from this playlist. The link will be given below in the description box. However, if you have seen that video, then I believe you remember that we also discussed that how the inverse of a matrix, in case that is possible to be calculated, helps us to solve for unknowns in a given linear equation. And that is pretty much it for the theory part. Now quickly let's jump into our Jupyter notebook, where we will also see some practical demonstration of calculating the determinant for a matrix with the help of NumPy library. So in this cell I'm creating this array X, which is nothing but a 2x2 matrix, and I'm using this function, which is numpy.linearalgebra.determinant, and then I'm passing our matrix as an argument, and as an output it simply provides us the calculated determinant for the given matrix. In the following example, I have considered a singular matrix that we have already seen earlier in this lecture, and when I try to calculate the determinant for this one, as expected the output will be 0. And in a similar way, you can calculate the determinant for a matrix of bigger size as well, for any given dimension, provided it has to be a square matrix. And for this one, we have already calculated the determinant manually that we have seen in the previous example, and yes, we use the same function again to get the expected output. And this is how simple it is to calculate the determinant using any specific library from a programming language. Now the most interesting part of this lecture, where we will try to understand the relationship between the determinant and eigenvalues. By the way, if you have not watched our lecture on eigenvalues and eigenvector, then I suggest that you watch it first and then come back to this point. But if you have already watched it, then let's continue from here. So determinant of a given matrix, let's say matrix X, is always equals to the product of all eigenvalues of X, which means let's say that we have a matrix X which has 4 elements. So let's say we have X1, X2, X3 and X4, and let's say the eigenvalues for this matrix is this val1 and let's say val2. In that case, the determinant of this matrix X will be exactly equal to the product of its eigenvalues, which is val1 multiplied by val2. This is exactly what this first pointer essentially means. And the second point says the determinant of X quantifies volume change to other matrix or vector after X is applied to it. Now this is the most important point to understand, so I will quickly erase all this and let's consider the example of matrix A. So I will quickly create it, and if we try to plot these vectors, it will look something like this. So starting from 0, 1 points towards x-axis and 1 point towards y-axis. And as we know, this particular matrix is representing some area on a two-dimensional plane, so it can be considered as a square surface. So this area is being represented by the matrix A. Now let's say we want to apply a matrix X to this other matrix A, and let's say that the determinant for this matrix X that we are trying to apply on matrix A is 2. Then it means that the matrix X, when it will be applied on matrix A, the size of the matrix A or the area covered by the matrix A will increase by double of its size. So this time if I'll have to draw the dot product of X and A, then it will be transformed something like this. So 2 points toward x, and let's say if we keep it 1 and 2, then 2 points towards x, and then 1 and 2, 2 points towards y. And if we want to measure this area, then this area will be double in size from the first one when we do a comparison. However, let's say that the determinant of this matrix X is not 2 but it is 0.5. Then it means that the area covered by the matrix A will now be reduced by half of the initial size. So this time this will be reduced to 0.5. So here let's say we keep it as 0.5 and this point is 1. And again towards y-axis this point is 1 and this is, let's say, 0.5. Then this will be the area represented by the matrix A after we have applied matrix X with it. And this time it will make more sense if you go through the second point again, which says determinant X. Let's say in our case we have determinant X here. It quantifies the volume change, which means the volume right here when it is changed to this volume. It is quantifying this volume to the other matrix or vector, which we have matrix A in our example, after applying X to it, which means after doing a multiplication. And now in order to have a further strong understanding on this relation between determinants and eigenvalues, we are going to see some practical coding demo on our Jupyter notebook. So we will start with the coding demo for the first pointer, which says determinant of X is always equals to the product of all eigenvalues of X. Let's try to prove the same on coding. So I have created a variable X, which is a 3x3 matrix, and I'm using this function that we have used earlier as well in order to calculate the eigenvalue and eigenvector for our matrix X. And when we check the eigenvalue, then for 3 columns of the matrix X, we get 3 eigenvalues respectively. And if we calculate the product of all the eigenvalues, we get this number. And also when we try to calculate the determinant of the matrix X, and if we take the absolute value, we get the same output as this one, which is proving our first point that determinant X is always equals to the product of all eigenvalues of X. Now let's try to prove the second pointer with coding that says determinant of X quantifies the volume change to other matrix after X is applied to it. So we will understand the impact of applying matrices with varying or changing values of determinant X. So for demo purpose, I have created this two-dimensional array A, which is a 2x2 matrix, and when we plot it, we get this figure. 1 points towards x-axis and similarly 1 points towards y-axis. And first we will try to apply a singular matrix on our matrix A. So I have taken the example of this singular matrix, and as you can see, the first column is the multiple of the second one, and when we try to calculate the determinant for this matrix N, we get 0. And it means this matrix N, when we will try to apply it on our matrix A, it is neither going to increase or decrease the area represented by our matrix. However, it will completely vanish the area to nothing. Let's try to understand how that works. So I will simply do a multiplication of the singular matrix N and our original matrix A, and we get this output, which is NA. And when I try to plot it, first I'm plotting the original matrix, which is matrix A, and then I'm plotting the output of A multiplied by N. So we can see a comparison here. So initially our matrix was representing this area, this rectangular surface. This area was represented by our original matrix. But after applying the singular matrix N, our matrix has been converted to these two vectors, this one and this one. And as you can see, both are pointing out to equal and opposite direction to each other, which means they are representing no area. So this area that we initially had has been vanished. And this is something what we need to understand. It actually happens when we are trying to apply a matrix which has a determinant of 0. It is going to squish the area of our matrix to 0. So initially it was representing some area, but after transformation, now it is representing no area. Which also means that if any one of the matrices eigenvalue is 0, in that case the product of all eigenvalues must be 0, because 0 being multiplied by anything will be result to 0. And since the product of all the eigenvalues is equals to the determinant of the matrix, then the determinant also has to be 0. Okay, now let's move forward to the next example. And this time we will try to apply an identity matrix, which is this matrix of 2 by 2 size in the variable I. And as we know, the determinant for this matrix, if you try to calculate, it will come out to be 1, which essentially means that it is going to make no changes with the area represented by our original matrix A. Although it may look a bit stupid because I am trying to multiply two identity matrices, which of course will provide no changes in the output. But still, the important thing which needs to be understood is that if we have the determinant of 1, in that case, that particular matrix, when it is multiplied with any other matrix, it will cause no changes to the area represented by that matrix. And finally, at the end, this one is my favorite example, and I just hope that this is going to be clarify all the questions and concepts around this topic for you. So I'm creating this A2 matrix which has these 4 elements, and when I'm trying to take the determinant for it, it comes out to be minus 1.5. The absolute value will be 1.5. And when we multiply this A2 matrix with our original matrix A, then we get this output. And let's try to understand the changes after this multiplication on the plot right in the next cell. So this was our first vector of the matrix, which was pointing towards x-axis at one point, and after transformation this gets flipped over the axis and now it is pointing towards the opposite direction. However, it is still on its span, which satisfies the condition of an affine transformation. And the other vector of the matrix, which was initially pointing at 1 point towards the y-axis, that is now pointing to -2 in the opposite direction. And if we try to observe the changes with the area of these two output, then what we will find out is that this area is exactly 1.5 times of the initial matrix after applying this A2 matrix, which has a determinant of 1.5. And that is all for today's lecture. I understand that there was too much content in this particular lecture to consume and understand. However, all these topics are very important to be known in order to have a fundamental concept and idea in the field of machine learning and data science. And anyways, we have covered all the fundamental and basic topics of matrix and vectors. So now it is also the time that we move out of our comfort zone and learn something exciting things further. That is it for today's lecture, and I will see you in the next video. Thank you very much for your time today. Goodbye and take care.